We feel stationary. Standing on the surface of the Earth, the ground beneath our feet feels solid, stable, and still. But this sensation is a profound illusion. Our planet is in constant dizzying motion, spinning on its axis at 1,000 miles per hour, while hurtling through space in its orbit around the Sun at 67,000 miles per hour. The Sun itself, along with its entire family of planets, is not stationary either. It is on a grand 230 million year journey around the colossal black hole at the center of our Milky Way galaxy, a journey it undertakes at a staggering 500,000 miles per hour. For decades, astronomers believed this was the full story of our motion, a nested series of predictable orbits within our home galaxy. But they were wrong. In the latter half of the 20th century, a series of baffling measurements revealed that our galaxy's journey is not that simple. The entire Milky Way, our magnificent spiral home, along with our closest cosmic neighbors, and even the entire supercluster of galaxies we belong to, is being pulled sideways. We are being dragged by a powerful and unseen current in the vast, dark river of space-time. We are being irresistibly drawn towards a single mysterious point in the cosmos, a place we cannot even see properly with our telescopes. It is a gravitational anomaly of almost unimaginable scale, a hidden titan whose mass defies easy explanation. For lack of a better term, astronomers have given this mystery a fittingly epic name: the Great Attractor. The story of the discovery of the Great Attractor does not begin by looking at galaxies, but by listening to the faintest and oldest echo in the entire universe. It begins with the cosmic microwave background, or the CMB. In 1965, two American radio astronomers, Arno Penzias and Robert Wilson, were working with a large horn antenna in New Jersey. They were attempting to use it for radio astronomy, but they were plagued by a persistent low-level background noise, a gentle hiss that seemed to come from every direction in the sky, no matter where they pointed their antenna. They checked their equipment, cleaned the antenna, even removing pigeon droppings they famously blamed for the noise. But the hiss remained. It was a cosmic static that they simply could not get rid of. What they had accidentally discovered was monumental. This hiss was not an error. It was the afterglow of the Big Bang itself. It was the faint residual light from a time just 380,000 years after the birth of the universe, when the cosmos had cooled enough for the first atoms to form, allowing light to travel freely through space for the first time. This ancient light, stretched out over 13.8 billion years of cosmic expansion into the microwave portion of the spectrum, permeates the entirety of space. The CMB is, in effect, a baby picture of the universe. The most crucial property of the CMB is its astonishing uniformity. The temperature of this background radiation is almost perfectly identical in every single direction we look, at a frigid 2.725 degrees above absolute zero. This uniformity is what makes the CMB the ultimate rest frame of the universe. Imagine you are floating in the middle of a perfectly still, featureless lake. If you are not moving, the water around you is the same everywhere. But if you start swimming, you will create a small wake, and the water in front of you will be slightly compressed, while the water behind you is slightly stretched. The CMB acts in the same way for motion through space. Due to a phenomenon known as the Doppler effect, if an observer is moving relative to the CMB, the light in their direction of travel will be slightly compressed to higher frequencies, making it appear infinitesimally hotter. This is a cosmological blue shift. The light in the opposite direction, from which the observer is moving away, will be stretched to lower frequencies, making it appear infinitesimally cooler, a cosmological redshift. This creates a pattern on the sky known as a dipole, with a hot spot in the direction of motion and a cold spot in the opposite direction. In the 1970s, as technology improved, astronomers set out to measure this dipole. They expected to find one, of course. They knew the Earth orbits the Sun, and the Sun orbits the center of the Milky Way. These known motions should produce a predictable dipole in the CMB. But when the results came in, they were baffling. The dipole they measured was significantly stronger than expected, and it was pointing in a slightly different direction than the one predicted by our galaxy's rotation. The implication was staggering. After subtracting all the known motions, Earth around the sun, sun around the galaxy, there was a huge residual velocity left over. The numbers were hard to believe. The data showed that our entire Milky Way galaxy, our local group of galaxies, including Andromeda, was being dragged through intergalactic space at a peculiar velocity of over 600 kilometers per second. That's a speed of more than 1.3 million miles per hour. This was not the stately, predictable motion of galactic rotation. This was a deviation, an anomaly. The entire galaxy was falling. The logical conclusion was unavoidable. Something massive, something with the gravitational pull of many thousands of galaxies, must be out there, hidden in the darkness, pulling us towards it. The hunt for the Great Attractor had begun. Finding the source of this immense gravitational pull was the next great challenge. While the CMB told astronomers the direction and speed of our motion, it couldn't tell them how far away the source was. To find it, they had to turn from the ancient light of the Big Bang to the light of the galaxies themselves and embark on one of the most ambitious mapping projects ever conceived. Their primary tool was a concept discovered by Edwin Hubble in the 1920s, the expansion of the universe. Hubble had found that, on the largest scales, every galaxy is moving away from every other galaxy, as the fabric of space-time itself stretches. Furthermore, he discovered a clear relationship. The farther away a galaxy is, the faster it is receding from us. This cosmic recession is known as the Hubble flow, and it can be measured by observing a galaxy's redshift, the stretching of its light towards the red end of the spectrum. Astronomers realized that this universal expansion could be used as a baseline. If the universe were perfectly uniform, a galaxy's redshift would be a direct and perfect indicator of its distance. But the universe is not uniform, it is lumpy. It is filled with vast clusters of galaxies and great empty voids. These lumps, these concentrations of mass, exert their own gravitational influence, causing galaxies to deviate from the pure, smooth Hubble flow. By meticulously measuring both a galaxy's distance, through other more complex methods, and its redshift, astronomers could calculate its peculiar velocity, the part of its motion caused by local gravity rather than the overall cosmic expansion. If a galaxy's redshift was slightly lower than predicted by its distance, it meant it had a peculiar velocity moving towards us, fighting against the Hubble flow. If its redshift was higher, it was moving away from us even faster than it should be, perhaps being pulled by something in that direction. This technique was the key, but it required an enormous amount of work. In the late 1980s, a team of 7 astronomers, who would become famously known as the 7 Samurai, embarked on a groundbreaking project. The team, which included prominent astronomers like Sandra Faber, Alan Dressler, and Donald Lyndon Bell, set out to systematically measure the distances and peculiar velocities of over 400 elliptical galaxies within our cosmic neighborhood. For years, they traveled to observatories across the globe, patiently gathering data, building a 3-dimensional map, not just of where galaxies were, but of how they were moving. When they analyzed their data, a stunning and coherent picture emerged. They confirmed that the Milky Way was not alone in its strange journey. Our entire local group of galaxies, including the massive Andromeda galaxy, was moving in the same direction. And beyond that, they found that the entire Virgo supercluster, the colossal structure of which our local group is just a tiny outlying suburb, was also being pulled along in this great cosmic current. The entire region of space for hundreds of millions of light years was flowing, and all the motion vectors, all the gravitational arrows, were pointing towards a single, concentrated region of space, about 150 to 250 million light years away, in the direction of the southern constellations of Hydra and Centaurus. They had found the location of the mass that was pulling us. Based on the scale of the motion it was inducing, they calculated that this Great Attractor must have a mass equivalent to tens of thousands of Milky Way galaxies concentrated in a relatively small volume of space. It was a stunning discovery, a new and previously unknown continent on the map of the cosmos. There was just one immensely frustrating problem. When they pointed their optical telescopes towards this newly discovered location, they could see almost nothing. The Great Attractor was hiding. The reason for the Great Attractor's invisibility is an unfortunate cosmic coincidence. Its location in the sky places it directly behind the densest part of the plane of our own Milky Way galaxy. This region of the sky is known to astronomers as the zone of avoidance. It is not empty. On the contrary, it is overwhelmingly full. When we try to look in that direction, our view of the distant universe is obscured by a thick, nearly opaque screen of gas, interstellar dust, and the blinding light of billions of our own galaxy's stars. It is like trying to see a distant mountain range through a thick, dense forest that is immediately in front of you. The very galaxy we live in was acting as a curtain, hiding the solution to the mystery of our own motion. For decades, this made studying the Great Attractor directly an almost impossible task. Optical astronomy was blind, but astronomers are ingenious, and they began to develop new techniques and new technologies to peer through this celestial veil. The first breakthroughs came from looking at the universe in different wavelengths of light. Infrared light, with its longer wavelength, is much better at penetrating clouds of dust than visible light is. In the late 1990s, projects like the 2-micron all-sky survey, 2MASS, began to systematically scan the entire sky in infrared. Peering into the zone of avoidance, these surveys started to reveal the faint, ghostly outlines of galaxies that had been completely hidden from optical telescopes. They were seeing the first hints of the massive structures that lay beyond. An even more powerful tool came from the field of radio astronomy. This technique relied on detecting a very specific signal, the faint radio waves emitted by neutral hydrogen gas, the most abundant element in the universe. Hydrogen atoms emit a characteristic signal at a wavelength of 21 centimeters. This radio wave passes through interstellar dust almost completely unimpeded. Radio telescopes, like the Parkes Observatory in Australia, could be pointed at the zone of avoidance, and they could hear the signal from the hydrogen gas within the hidden galaxies. This was more than just a way to detect a galaxy's presence. By measuring the precise Doppler shift of this 21-centimeter radio line, astronomers could determine a hidden galaxy's velocity with incredible precision. This was the key that unlocked the zone of avoidance. A team of astronomers, led by René Kraan-Korteweg, embarked on a years-long project to painstakingly scan the region of the Great Attractor with radio telescopes. What they found was the smoking gun. As they mapped the hidden galaxies, they uncovered a colossal supercluster of galaxies, a previously unknown metropolis of stars, sitting right in the heart of the region where the Great Attractor was predicted to be. This structure, known as the Norma Cluster, is a massive and dense collection of galaxies, with a mass of at least 1,000 trillion suns. It was a huge concentration of visible, or at least detectable matter, that could account for a significant portion of the gravitational pull that the Seven Samurai had detected. The Norma Cluster appeared to be the core, the very heart of the Great Attractor. The mystery seemed to be solved, but as astronomers gathered more and more data, a new complication arose. The Norma Cluster and its surrounding supercluster were indeed massive. The next clue in the story had actually been discovered decades earlier, but its significance was not yet understood. In the 1930s, the great American astronomer Harlow Shapley had been studying photographic plates of the sky and had noted an enormous cloud of distant galaxies, a remarkable concentration located far beyond the Great Attractor, but in the same general direction. For decades, this was just a curiosity. But as the mystery of the Great Attractor deepened, astronomers turned their attention to this distant structure. What they found was staggering. The Shapley supercluster, as it is now known, is the largest and densest concentration of galaxies in our local universe. Located about 650 million light-years away, it is a cosmic behemoth, a gravitational monster containing more than 8,000 galaxies with a total mass of over 10 million billion suns. A new, more complete picture began to emerge. The Great Attractor, centered on the Norma Cluster, is the nearest major gravitational well to us. It is like a large valley into which our local group is currently flowing. But the Great Attractor itself, along with our entire Virgo supercluster and other neighboring structures, is also being pulled downhill in the same direction, towards the even deeper and more massive gravitational valley of the Shapley supercluster. Our motion is not a simple journey to one point, but part of a grand cosmic flow, a multi-stage cascade of matter towards the densest and most massive region of the local universe. This new understanding culminated in a groundbreaking study published in 2014. A team of astronomers led by Brent Tully proposed a new way to define our place in the cosmos. They argued that superclusters should be defined not as just loose collections of galaxies, but as gravitational basins. They mapped the peculiar velocities of over 8,000 galaxies in our cosmic neighborhood, tracing the paths that they were all flowing along. They found that our Milky Way galaxy is part of a vast supercluster, a continent of 100,000 galaxies, all flowing towards a common gravitational center. They named this structure Laniakea, a Hawaiian name that means immeasurable heaven. Within this framework, the Great Attractor is not a separate, mysterious object pulling us from afar. The Great Attractor is the gravitational center of Laniakea. It is the valley floor of our home supercluster. We are not being pulled towards it as if by a tractor beam. We live inside the gravitational basin that it defines. We are simply following the contours of space-time, flowing downhill towards the center of our own vast cosmic home. To complete the picture, astronomers have even found the opposite of an attractor. By mapping the cosmic flows, they have identified a large, mostly empty region of space, a great void located in the opposite direction of the sky. This region, nicknamed the dipole repeller, exerts a subtle but significant gravitational push. It is not an anti-gravity force, but simply the result of there being very little matter in that direction to pull us back. So our galaxy's final peculiar motion is the result of a cosmic tug-of-war. We are being pulled towards the dense region of the Great Attractor and the Shapley supercluster, and simultaneously being gently pushed from behind by the emptiness of the dipole repeller. The mystery of the Great Attractor, a journey that began with a faint hiss of static from the dawn of time, has led us to a profound and beautiful new understanding of our place in the universe. We are not an isolated island galaxy adrift in an endless ocean. We are a tiny, infinitesimal part of a vast, interconnected cosmic web, a magnificent structure of filaments, clusters, and voids, all shaped and orchestrated by the invisible hand of gravity on the grandest of all scales. We now know that we live within the boundaries of a supercluster called Laniakea, and that we are flowing along with 100,000 other galaxies towards a gravitational heart we can barely see. The journey of our galaxy through space is a testament to the awesome and invisible power of gravity and to the relentless human quest to map the dark, hidden continents of our cosmos.